In the vast expanse of the cosmos, two planets, mirror images of each other, gracefully orbit their respective stars. One, Earth, a celestial oasis teeming with life in myriad forms, from the smallest bacteria to the mightiest whales. The other, Venus, a world shrouded in mystery and inhospitable conditions that make it a challenge to even imagine, without a shiver of discomfort. Venus, a twin in size and mass to Earth, shares a similar chemical composition, but its surface is a far cry from the beautiful blue planet we know. The atmosphere of Venus is saturated with sulfuric acid, a corrosive substance that would blind any colonist, and the pressure at the surface level is more than 90 times that of Earth. Temperatures on Venus can reach up to 475 degrees Celsius, with lead compounds melting under such extreme heat. Any attempt to land a probe ends in the death of the apparatus within hours. Yet, according to modern climate models, Venus could have retained significant reserves of liquid water on its surface for up to 2 billion years. Under those conditions, oceans similar to those on Earth may have raged, and the temperature and pressure were quite comfortable for the emergence of biochemical reactions. This intriguing possibility leads us to delve deeper into the enigma that is Venus. We explore the planet's past with the three components of the conditional equation of life on Venus, which breaks down the most complex problem into three simple questions: the origin of O, the stability of R, and the continuity of C. Each of these quantities is estimated from 0 to 1, expressing the probability that life could have arisen at all, how much it could have spread and diversified, and whether there was ever a time and place on Venus suitable for life, even up to the present day. The first parameter of origin poses the question: did conditions for abiogenesis, the spontaneous transition from chemistry to biology, ever exist on Venus? We know that in its young era, powerful streams of sunlight reached Venus. Volcanoes were active, throwing out heat and chemical elements, and there was something to assemble the simplest organic molecules, the building blocks of life, consisting of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The second parameter, resilience, is a kind of survival cheat code. If life did arise, was it able to take hold, become stable, and diversify? On Earth, we see how the biosphere adapts to ice ages, mass extinctions, floods, and droughts, filling up with new forms of life without human intervention. On Venus, volcanic activity probably emitted gigantic streams of sulfur and carbon dioxide into the atmosphere, creating a continuous greenhouse engine that gradually brought temperatures and pressures to fatal levels. The last and perhaps most dramatic parameter is continuity, which asks us, was there anywhere and at any time on Venus a place suitable for life, right up to the present day? Once the greenhouse collapse wiped out the oceans, life, if there was any, was doomed. Modern analyses of volcanic gases show that even with today's activity, water makes up no more than 6% of the volume of emitted gases, indicating an extremely meager reservoir of H2O in the planet's interior. If, on the way from the ancient oceans to our missions, even one condition became completely inhospitable, C, as well as the entire probability L, is zeroed out. But there is another important layer of knowledge. This is the experience of our predecessors, the first interplanetary messengers to Venus. The Soviet series of Venera probes, launched from 1961 to 1985, became a veritable operating system for studying its atmosphere and surface. Venera 4, which descended through the clouds in 1967, measured the atmosphere for the first time, recording it as 95% CO2 and small amounts of nitrogen and water vapor. Venera 7 was the first to transmit surface temperature and pressure data in 1970, recording 465 degrees Celsius and 90 atmospheres. Venera 9 and Venera 10 returned the first black and white panoramic images of Venus's boulder-strewn landscape in 1975. Although the romantic hopes of the Garden of Eden were dashed forever, these devices laid the foundation for all subsequent research. Almost 4 decades later, 3 space missions are heading to Venus to shed light on the remaining questions. NASA is preparing the Da Vinci mission, which will launch an atmospheric umbrella and make the first direct measurements of the composition of the air from the top of the clouds to the surface in 40 years. Da Vinci will be the first mission to combine 2 flybys and a lander, and is expected to reveal the truth about the presence of oceans and continents on early Venus. The European Space Agency ESA officially developed the Veritas mission in January of this year, with launch scheduled for 2031. Veritas will create detailed 3D terrain maps, track current volcanic activity, and use radar probes to probe the structure of the planet's interior to see if it continues to churn up the atmosphere with volcanic emissions. New data has already been published, including the first direct measurements of chlorine oxide CgO in the Venusian atmosphere. These measurements show its distribution by altitude and seasonal variations. This discovery is important because CgO is involved in oxidation processes and can affect the stability of aerosol layers, and therefore the planet's thermal balance. A large-scale study that applies a quantum approach to modeling the evolution of the Venusian atmosphere, including the dynamics of CO2 samples and sulfur compounds, has also been conducted. This study showed that pinpoint eruptions that released huge volumes of gas over short periods could have accelerated the planet's transition to its current state, leaving scars on the ancient climate. Theoretical and laboratory experiments continue, with researchers modelling sulfuric acid droplets, treating them with special microbes, and finding out whether terrestrial organisms are able to survive at temperatures up to 120 degrees Celsius and extremely acidic conditions. These experiments give hope that similar life forms could live in the cloud layers of Venus at an altitude of about 50 kilometers, where the pressure and temperature are close to those of Earth. As we have seen, the collected data and the missions being prepared are gradually refining the parameters of the planet. If O is close to 1, this means that the conditions for the origin of life once actually existed. A high AP will indicate the ability of the biosphere to withstand volcanic and climatic cataclysms, and 0C will leave a chance to find traces of these organisms today, possibly in clouds or in thin layers of aerosols. By studying Venus today, we are learning to read the code of the evolution of Earth-like planets. Every new drop of sulfuric acid, every photo taken or captured, and every Cg atom detected in the atmosphere brings us closer to understanding how the frequency and scale of greenhouse collapses affects the habitability of worlds beyond our solar system. And perhaps one day, analyzing data from a descending probe, we will find microscopic traces of metabolism, a direct answer to the question, are we alone in the universe? Once ignored and shrouded in mystery, Venus is now becoming our learning ground and beacon for the search for life beyond Earth. It reminds us that even identical twins can behave differently, and that the choice of a small variable in the climate equation can have dire consequences for the entire planet. But there is still a chance to unravel its secrets, and perhaps it is there, in the dense acid clouds, that clues to the origin of life and how fragile and at the same time amazing our own planet is lie.